For this problem, we're told we have a balanced three-phase load with a load apparent power of 15 megavolt amps and a power factor at the load of 0.85 with a 115 kV line voltage at the load and also a series line impedance. And we need to determine the current as well as some other things. We're not told otherwise, so we're assuming this is going to be a Y connection. I'm going to draw the generator first. So we'll have the three phases of the generator. Each of these will go through the series line impedance. And these will all go to the Y connected load. I'll call each of these ZY. Now, because this is a balanced Y connection, we can look at just one of the phases. So it'll look like this. We'll have the voltage and then two series impedances, Z line and ZY. We're given a voltage across ZY as 115 kV, but since down here is neutral, we want the phase voltage instead. So it'll be 115 divided by the square root of 3, which is 66.4 kV. We were given an apparent power of 15 megavolt amps with a power factor of 0.85, and we were told this is lagging. The formula for three-phase apparent power is 3 times V phase times I phase conjugate. We were only given the magnitude of the three-phase apparent power, so if we want the angle as well, we'll have to take cosine inverse of the power factor, which is 0.85, and that's going to give us 31.8 degrees. So S three-phase is going to be 15 at an angle of 31.8 degrees megavolt amps. V phase was 66.4, and we're just going to assume this is A, so at 0 degrees kilovolts. So back in this equation, if we want to solve for I phase conjugate, that's going to be S three-phase divided by 3 times V phase. So S will be 15. I'll do times 10 to the 6 for megavolt amps with an angle of 31.8 degrees. I'll divide that by 3 times V phase, which was 66.4 times 10 to the 3 for kilovolts at 0 degrees. And this is 75.3 at 31.8 degrees with units of amps, but this was I phase conjugate. So we're going to need to invert this angle to get I phase, which will be 75.3 with an angle of negative 31.8 degrees. The problem wanted the line current, but in a Y connection, the line current is the same thing as the phase current. So the line current is also going to be 75.3 at an angle of negative 31.8 degrees. So that is the answer to part A. Part B wanted the power loss of the line impedance. So this is just going to be I squared times R. They gave us C of the line was 50 plus J times 100 ohms. We don't care about the imaginary part. We only care about this real part. So it'll be I squared. It's going to be I line times 50. So it's 75.3 squared times 50, which is 283,513.6 watts. This is only the power loss of a single phase. So if we want the three-phase power loss, we'll just take this and multiply by 3. And we'll get 850.541 kilowatts. So that's the answer to part B. Part C wanted the angle of the power factor. We already found this above. We took cosine inverse of 0.85, and that gave us 31.8 degrees. And that's our answer for part C. Part D wants the line to neutral at the receiving, which is just going to be V phase. We already found this was 66.4, and again we got this just by doing 115 divided by square root 3. So V phase will be 66.4 kilovolts. So that's the answer to part D. Part E wanted the voltage drop due to the line. So this will be I times Z, and Z was 50 plus 100 J ohms. The magnitude of Z will be the square root of 50 squared plus 100 squared, which is 111.8. The angle will be tangent inverse of the imaginary part, which is 100, divided by the real part, which is 50. That will be 63.4 degrees. So Z will be 111.8 with an angle of 63.4 degrees. And I is the line current, which is 75.3 with an angle of negative 31.8 degrees. So to find V line, we can just multiply these two values. It's 111.8 times 75.3 with an angle of 63.4 minus 31.8. So it's 8,418.5 with an angle of 31.6 degrees. So V line will be 8.42 with an angle of 31.6 kV. So that's the answer to part E. And lastly, for part F, we want the V line of the sending side, so the generator. Well, if I draw this schematic again, we'll have the line impedance in series with the load. This line impedance had a voltage drop of 8.42 with an angle of 31.6 degrees kV, and the phase voltage of the load was 66.4 with 0 degrees kV. So if we want to find the V line of the gen, we can just add these two values. We'll have V phase of, I'll call it line, plus just V phase of the load. And we want the line, so we're just going to multiply this by the square root of 3. Because V phase of the line has an angle, I'm going to need to split this into its imaginary and real part. So it's 8.42 kV times cosine of 31.6 degrees plus J times sine of 31.6 degrees. This cosine becomes 0.852, and this sine becomes 0.524. Both of these will be multiplied by 8.42 kV, so it's 7.17 plus J times 4.41 kV. So now we have V phase of line, and V phase of load is just all real. So V line of the generator will be 7.17 plus 66.4 plus J times 4.41. So that's 73.57 plus J times 4.41. All that will be multiplied by square root of 3. First, I need to determine the magnitude of this. So it'll be 73.57 squared plus 4.41 squared. All that will be square rooted. That is 73.7 kV. We'll multiply this by root 3, which is 127.66 kV. Now for the angle of this, it'll be tan inverse of the imaginary part over the real part. So 4.41 over 73.57, which is 3.43 degrees. So V line of the generator will be 127.66 with an angle of 3.43 degrees kV. So that's the answer to part F. Now that we solve everything, that's the end of this video. So if this video helped you, consider subscribing.